Alright, thanks for watching and welcome to our 11th installment of the Gaussian integral. And this one is for complex analysis aficionados, because you may say there must be a complex analysis way of doing the Gaussian integral, and indeed there is. And as usual, I would like to thank Keith Conrad for coming up with those great notes. They're just based on those notes. So, here's the complex way. Step 1. Consider the following function. And if you're curious where this function comes from, just stick around till the end, and at the end I'll explain how I found this function. So, let f of z be e to the minus z squared over 2 over 1 plus e minus tau z. Just a homage to Terence Tao. So tau is square root of pi 1 plus I. So consider this almost Gaussian function where tau equals to this. And what we would like to do, we would like to integrate this function over the following rectangle. A rectangle of the following form. This is minus r, this is r, minus r plus I squared root of pi, and r plus I squared root of pi, where r is very large. Alright, and to do this we need to find the residues. So let's first of all determine if there's even a singularity in this rectangle. Indeed there is, because note, when is there a singularity? It's if, this denominator is 0. So when is that denominator 0? So 1 plus e to the minus tau z equals to 0. That tells you e to the minus tau z equals to minus 1. And 1, remember, it's e to the pi I, but with multiples of pi, odd multiples of pi. So let's write it as 2m plus 1 because of Peyam. And then what we get is, of course, minus tau z equals to pi I 2m plus 1. So z equals to minus pi I over tau 2m plus 1. But if you use now the definition of tau, turns out 1 over tau, you can write it as follows. And in the end, you get minus pi I 2m plus 1, 1 over square root of pi. So 1 over square root of pi. And the 1 over 1 plus I is just 1 minus I over 2. And notice, indeed, if you think about it, you could rewrite this in terms of tau, because I times this then just becomes, let's see, minus square root of pi over 2m plus 1 times I plus 1. And notice you have precisely this square root of pi and this I plus 1, which gives you tau. So minus tau over 2 times 2m plus 1. So, what are where are the singularities? I believe they're on a line, and in particular, it's just odd multiples of minus tau. So, in other words, odd multiples of tau divided by 2. So, for example, stuff like tau over 2, and then minus tau over 2, 3 tau over 2, etc., etc. And it turns out in this rectangle, where the imaginary part is between 0 and square root of pi, there is just one singularity, the one at tau over 2. That's why we chose that rectangle to be kind of thin, if you want, in height. And so, all we have to do is we integrate over those 4 parts, and it equals to like 2 pi I times that residue. So, first of all, if C is the whole contour, then step 2. The integral of c of f of z dz is 2 pi I times the residue at z equals to tau over 2 f of z. And it turns out, notice f is just a ratio of two things. Okay? And there's just one singularity here. So it turns out if you have fractions p over q, then turns out if there's just one residue and the denominator and the numerator are nicely behaved, you just plug in p of 0 and q prime at z0, where z0 is a singularity. So here it just gives you 2 pi I e to the minus tau squared over 8 of minus tau e to the minus tau squared over 2. And you can just rewrite this as follows: 2 pi I, so minus tau squared over 8 over tau squared over 2 becomes 3 tau squared over 8. And minus tau is just minus square root of pi times 1 plus I. And lastly, you just using the definition of tau, which I kind of wrote here, tau is square root of pi times 1 plus I. It turns out that this whole gibberish just simplifies to square root of 2 pi. How nice is this? And I leave it up to you to do the calculation, because you'll see already without this, the formula is pretty long, okay? So, that gives us the integral over the whole contour. Now, all we need to do is to integrate it over those four parts, A, B, C, D. So yeah, we'll be here for a long time, because we have to do 4 things, but not that bad, you'll see. So, again, this is our function, this is our contour. So first, let's do part A. So let's see, I think that's step 3. So let's integrate over the region A. So f of z dz. That's not too bad to do, because you can just parameterize the path as gamma of t equals to t, and it becomes integral from minus r to r e to the minus t squared over 2 of 1 plus e to the minus tau t dt. And as r goes to infinity, this gives us integral from minus infinity to infinity e of minus t squared over 2 and 1 plus e to the minus tau t dt. Which is surprising. It's not quite the Gaussian integral, but just wait for it. And then somehow, miraculously, you'll see the Gaussian integral appears. Okay, second part, do the part B. And I want to show you that basically on the vertical lines, the integral just goes to 0 asymptotically. So, step 4. So on the one hand, we get an integral which doesn't seem Gaussian at all. Now we want to show the second integral goes to 0. So step 4. And for this, as usual, let's just estimate it. Now, notice all we need, we start from r, and we just go vertically up to the imaginary unit, up to r plus I squared root of I pi. So here gamma of t is just r plus it. Shout out to Rochester Institute of Technology. Okay, RIT. And we get integral from 0 to square root of pi e to the minus r plus it squared over 2. And then 1 plus e to the minus tau r plus it. And then still this I dt comes from the derivative. And you just use the triangle inequality that's less than or equal to integral from 0 to square root of pi e of, let's expand it out, minus r squared over 2 minus rit, and then plus t squared over 2, and absolute value of 1 plus e to the minus tau r plus it dt. Now, notice this part is purely imaginary, so it goes away. So this part, the whole thing becomes 1, so that goes away in absolute value. And also, well, t is bounded, right? It's between 0 and square root of pi. So if you let r goes to infinity, the numerator goes to infinity. So this goes to 0, and it would be a problem if the denominator goes to infinity, but quickly let me show you why it's not the case. So 1 plus e to the minus tau r plus it. Well, because you want to show it's greater than something, you have to use this reverse triangle inequality. So it's bigger than absolute value of 1 minus absolute value of e of this. So minus tau r e to the minus tau it. And this becomes, so 1 minus e to the minus, let's see, let me just check something. So, okay, tau. Yeah. Remember, tau was square root of pi 1 plus I, so that becomes square root of pi plus I square root of pi. Now, in particular, e to the minus tau r becomes e to the minus square root of pi, e to the minus I, pi r, e to the minus I square root of pi r. Now, in absolute value, this is 1. And this term, well, it just goes to 0. So this becomes 1 minus e to the minus pi r. And absolute value of e to the minus tau it. And remember, t is bounded. So there's no issue of it, being, I guess, you can also calculate it explicitly, and you'll see this term has no problem. So in particular, as r goes to infinity, this goes to 0. And in particular, this term eventually will be greater or equal to 1/2. So in particular, this term will never be 0. So you have a term that goes to 0 over some strictly positive term. So in the end, this whole integral will go to 0 as r goes to infinity. Okay. So that's good. We're halfway done. We took care of this part. We took care of this part. And now let's take care of part C. C, senor. Okay. So, oh, not again. Okay. So, step 5. Step 5. Let's integrate f on this big part. All right. Integral of c, f of z, dz, and here the path is slightly more complicated. So you start at r plus I squared of pi, and you're essentially subtracting t from the real part of this. So gamma of t becomes r minus t plus I squared of pi. Because notice at 0, this becomes r plus I squared of pi. And at r, t equals to pi, 2r, this actually becomes minus r plus I squared of pi. So what this becomes, it's the integral from 0 to 2r of e to the minus r minus t plus I squared of pi squared over 2 over 1 plus e to the minus tau r minus t plus I squared of pi. So I just use the definition of f and I plugged in z equals to this monstrosity. And last but not least, we need a gamma prime, which becomes minus 1 dt. Okay, now you notice this is already very ugly. Let's just, especially because of this r minus t, let's just use a u sub to sort of make this r minus t disappear and make this more symmetric. So u is r minus t, then you know du is minus dt, and u of 0 is r, and u of 2r is minus r. So in the end, what we get is the integral from r to minus r of, so let's see, e of minus t plus I squared of pi squared over 2, and 1 plus e minus tau 1 plus I squared of pi, sorry, t plus, so not 1 but t. Okay, and minus dt, but minus dt is just du. So we're good here. And in particular, if you let r go to infinity, you get a following very strange integral. You get the integral from infinity to minus infinity of e, let's see, well this, e of minus t plus I squared of pi over 2 over 1 plus e minus tau 1 plus I squared of pi d. I just used, I just plugged in t for you. So I did the change of variable t equals to u. And also, well, we have infinity to minus infinity. That's kind of ugly. Let's just reverse this with a minus sign. So indeed it becomes minus the integral from minus infinity to infinity of this horrible thing. Okay? So what do we have? Well, a becomes some weird integral. B goes to 0, C becomes an even weirder integral, and now let's do D, and for D, exactly the same thing as here. We want to show that laterally, the function goes to 0, so I guess the integral goes to 0, and I'm just going to sketch it because it's really almost the same as before. So step 6. So let's estimate the integral of f of z dz. Again, here you want to go down from r plus I squared of pi to minus r. So you just use here the path gamma of t is minus r plus I squared of pi minus it. So this equals to absolute value of the integral from 0 to square root of pi e to the minus r plus I squared of t minus it squared over 2 over 1 plus e of minus tau minus r plus I squared of pi minus it, and then minus I dt. Again, the absolute value goes in, and then absolute value of minus I is just 1. And in the end, what you get is integral from 0 to square root of pi, just as before, e to the minus r squared over 2 plus some junk, and some, I think, real positive junk or something. 1 plus e to the tau r plus junk dt. And as r goes to infinity, right? This thing, because it's e to the minus r squared over 2 plus other, maybe complex or real junk, this actually goes to 0. And the only problem is, what about the denominator? But the denominator is 1 plus e to the tau r plus some junk. And in this case, you use the other triangle inequality. So in this case, you write it as this minus minus, so e to the tau r plus junk minus minus 1, and that's greater or equal to absolute value of e to the tau r plus junk minus 1. And notice as r goes to infinity, the real part is bigger than, at least bigger than 1. So in particular, this whole thing, at least it's greater than, let's say, 1/2. Even 1, I think. Okay, because again, r goes to infinity, so it might even blow up to infinity. So in particular, this denominator is never 0, so we get something that goes to 0 over something positive. So also laterally, the integral goes to 0. All right, so the good thing is now we have completed the 4 tasks. So it's like in Zelda, you got the 4 amulets and see what happens. Now we can sort of open the Triforce. Okay, so step 7, just add all of them together. So on the one hand, from part A, we get integral from minus infinity to infinity, e of minus t squared over 2 of 1 plus e to the minus tau t. B goes to 0. C gives us the following integral, if you remember. Integral from minus infinity to infinity, e of minus t plus I squared of 2 squared over 2, and 1 plus e of minus tau t plus I squared of pi. D gives you 0. And last but not least, the whole thing is 2 pi I times the residue, which we found to be equal to square root of 2 pi. Now, what in the world does it have to do with the Gaussian integral? It turns out, you'll see in a second, we'll be able to factor out the Gaussian integral from that. And for this, what would be nice is somehow to write this I squared of pi in terms of tau. And you'll see why it's so useful. So remember, tau is square root of pi times 1 plus I, which is square root of pi plus I square root of pi. So I square root of pi is just tau minus square root of pi. So really, what this integral, those two integrals become, we just get integral from minus infinity to infinity. This is f of t, dt, and minus integral from infinity to infinity. Now it turns out this is just the same as, so remember I tau, I square root of pi is tau minus square root of pi, and this is tau minus square root of pi. So this is just the same thing as f of t plus tau minus square root of pi dt equals to square root of 2 pi. Okay, now if you just use a substitute, so notice it's much easier, much cleaner written out this way. And now notice you can just use a substitution, u equals to, if you want, t minus square root of pi, and just shift it. Then it turns out we can just not think of this minus square root of pi. Okay. And we get integral. Let's see, no, I do need many more whiteboards. We're actually not quite done. Because I want to show why this is true. And I want to explain why we have this weird function f and this weird constant tau. So after this change of variables, you just get integral from minus infinity to infinity. F of t minus, technically f of u plus tau, but let's just let u be t. So f of t plus tau dt equals to square root of 2 pi. Turns out you can simplify this. Let me show you how. F of t minus f of t plus tau. That's e of minus t squared over 2 over 1 plus e of minus tau t minus e of minus t plus tau squared over 2 over 1 plus e of minus tau t plus tau. Then, well, notice this kind of involves e of minus t squared over 2 because it's e of minus t squared over 2, e of minus t tau, e of minus tau squared over 2. So, and in particular, here's what makes this work. There is, in fact, this common factor of this Gaussian integral. So, e of minus t squared over 2 of 1 plus e of minus tau t minus e of minus t tau, e of minus tau squared over 2, and then 1 plus e of minus tau t plus tau. And now, here is why we use the definition of tau. So you've seen tau was pretty important so far, but here it becomes crucial because tau squared equals to pi times 1 plus I squared. Remember what tau was? Tau was, let me see, anywhere here, oh well, let me check again. Well, tau was just square root of pi times 1 plus I. So tau squared is already this, and that simplifies in this e part. So e of minus tau squared over 2. That then just becomes, so 1 plus I, it turns out, then just simplifies to 2i. So we get just e to the minus pi I, which is just minus 1. So that's already nice here. This term just becomes minus 1. And also notice we get here e of minus tau squared. But e of minus tau squared then also simplifies to e of minus 2 pi I, which is 1. So, lo and behold, what we're left with here, and again, this is why it works. We get e of minus t squared over 2. 1 plus e of minus tau t. Minus minus, so plus e of minus tau t over 1 plus, so this is just 1, e of minus tau t. Sorry, this is a t, not a 1. And so all the bad terms, if you want, go away. And even better, this is 1 plus e of minus tau t. Well, it cancels out with 1 plus e of minus tau t. So in the end, we get e of minus t squared over 2. So this f of t minus f of t plus tau just becomes e of minus t squared over 2. And in the end, we get indeed, that's why I love complex analysis, e of the Gaussian integral, at least with this factor of 2, equals to square root of 2 pi. Oh my god! Can you imagine? We had this weird function here. We integrated them in 4 parts, right? We got some weird identity here. And it turns out this weird thing simplifies so that our Gaussian integral pops up. I think it's one of my favorite ways. It's even better than the multivariable way. Okay, so if you like, we're done. If not, just stick around. Let me tell you why I chose this function. So why f of z equals to e of minus z squared over 2 of 1 plus e of minus tau z. Okay, again, what we would like is as follows. So what's the thing that helped us? We still wanted to integrate over that rectangle. So r, suppose we don't even know the square root of pi. So minus r plus ib, minus r plus ib. And as before, suppose we want to integrate it over this rectangle. Now, one of the requirements that really helped us is that f goes to 0 here and here. So suppose what we need, first of all, is a function that goes to 0. Goes to 0 here. Okay. Then, same as before, what did this first integral give us? It gave us integral from minus infinity to infinity of f of x dx. That second integral, if you calculate it, again, it gave us the integral of f of x plus ib dx, but from infinity to minus infinity. And what is the whole integral? It would give us 2 pi I times the sum of residues. So we don't even require that there's just one residue. Then, what we get, notice we can switch the infinity and minus infinity, and in the end we would get integral from minus infinity to infinity of f of x minus f of x plus ib equals to something. Now, ideally, okay, we would like, and again that's dx, we would like this thing to be the Gaussian integral. So it would be nice if f of z minus f of z plus ib were equal to our Gaussian integral. And let's see, I don't think this was true in this case. Maybe it is. It was not true in this case, because notice this is not of the form ib. This is of the form tau. So in particular, this is too much to hope for. In general, you can't really find a function like that. Instead, let's try something different, okay? Let's try the following. Not that f is e to the minus z squared over 2, but f is equal to e to the minus z squared over 2 over some other function. Okay? Try that. And so this is our ansatz. And also, instead of doing that, let's assume something slightly more general, and the thing that helped us, f of z minus f of z plus tau equals to e of minus z squared over 2. Because that's indeed the stuff we had before. So even though this is too much to hope for, it might work with this tau. Then, let's try to plug in this ansatz. And, tau is to be determined. If you plug in this guess into this equation, you get the following. Then we get e to the minus z squared over 2 over dz minus e to the minus z plus tau squared over 2 over d of z plus tau, which you can just write as 1 over dz minus e of minus tau z minus tau squared over 2 over d of z plus tau equals to e of minus z squared over 2. Now, first of all, those terms cancel out, so that's very good. And remember, we will still want to find tau, and we also want to find d. Now, in general, this is still too hard to solve. So let's just do one more simplification. So let's suppose that actually d is periodic. So suppose d of z equals to d of z plus tau. Then those two terms are the same, so we can factor it out. 1 over dz times 1 minus e of minus tau z minus tau squared over 2 equals to 1. So d, I'm getting dz as well, okay? E of minus tau z minus tau squared over 2. All right. So if d were true, then we get this, okay? D is this, and one more thing. So this is our function d of z. So once we found tau, we would be done. And now the question is, what does this imply in terms of this function d of z? It turns out d of z equals to d of z plus tau. If you actually plug this into this formula, then we get at the end that e of tau squared equals to 1. And 1, remember, it's e of 2 pi im, e2 pi mi. Then we get tau squared equals to 2 pi im. And therefore, just picking out the easiest one, let's say with m equals to 1, so let's say 2 pi I, then tau becomes square root of 2 pi I. And if you take the principal square root, that just equals to square root of pi 1 plus I. Because that's square root of 2 pi e to the I pi over 2. So square root of 2 pi e to the I pi over 4. With possibly some other factors. But you can check indeed that tau squared equals to 1. 1 second. Yeah, you can check that e of tau squared equals to 1. Let me actually check it, because I'm not convinced. So, yeah, sorry. E of tau squared equals to e of pi, and then 1 plus I is like a 2i. So indeed, e of 2 pi I, which is 1. So that's good. So first of all, this gives us our tau, and then this would give us our d, and finally it would give us our f, because what is f? F of z equals to e of minus z squared over 2 over d of z. And it turns out if you do that, then you get e of minus z squared over 2 over 1 plus e of minus tau z. And that's precisely where you get this function. So it's neat. There's not only complex analysis, but I also show you how to get this function. So it's very, very cool. And if you like that and you want to see more math, please make sure to subscribe to my channel.